So now that we've looked at 7.2, the dot product, we're going to look at now, of course, applications of the dot product. So key ideas is just like we just talked about in 7.2, we discussed mechanical work already. So mechanical work is an application of the dot product. So work, which now we're just going to call W instead of writing out the full mechanical work, is completed when you're moving an object through a displacement. And just in this example, we're going to call that displacement vector S. And you're under an applied force. So you have a displacement, you have a force, and then you're acting at an angle of theta to the displacement vector. So if you have an angle, you have a force, you have a displacement, your mechanical work formula is equal to the force vector dotted with the displacement vector. So the force acting on an object dotted with the displacement vector. If we're talking about, here I'll just write beside it, Cartesian vectors. And you know you have a Cartesian vector if you're dealing with square brackets, right? So let's write here, Cartesian vectors. Which is also equal to the magnitude of the force vector multiplied with the magnitude of the displacement vector times cos of theta if we're talking about geometric vectors. Okay, so now we're going to talk about vector projections, which basically, just like it says here, is we're talking about shadows that are being placed with one vector being projected onto another vector, hence for vector projections. So just to move this up so you can see everything. So the arrows here are representing light, right? That's coming from above. That would be creating the shadow. So we have three different cases here that we're going to get to. So case one is if the angle between the vectors is less than 90. So it is important that you know the distinction here. So if your theta here, you can see an example like this, it would be less than 90, then the projection of V onto U, right? This is your projection vector of V. It's being projected onto U. U is actually the black one. If you can kind of imagine in behind, you can see that would be the tail, that would be the head. You can see the arrow there, which is written as, again, and read as the projection of V onto U. I'm projecting V, kind of you skip it at first, projecting V onto U. And what you're projecting onto is kind of the subscript there. Is the vector component of V in the direction of U, I guess, so I've already said that. So this is when theta is less than 90. I don't think I need to write that out, if you can just highlight it there. And the gray vector is the horizontal component of my projector vector being projected onto the ground, right? That's your shadow, basically, that would result. So because this projection vector is longer, right? When it comes down, you would just go vertically down. It's projecting that type of shadow on the U vector. Okay, so gray is our shadows. Whereas with case number two, if the angle between the vectors, right, the angle between the two vectors that I have, my ground vector, if you will, my projection vector, if it's between 90 and 180, as you see here, is only up to 180. That's all we're looking at in these cases. The direction of the projection of V, again, onto U, V is being projected onto U, but it can't directly be projected onto U if it's going past 90 degrees, then it's going to be projected, it's the opposite to the direction of U. The shadow that's going to be cast is having the U vector kind of going in the opposite direction, right? So that result would be negative. So you will always get a negative result if you're between 90 and 180. And basically your shadow is technically not going on top of the vector, but it's going in the opposite direction of the vector. And that would be the length of the shadow there. And the last case, if the vectors are perpendicular, so I have perfectly horizontal, perfectly vertical, then there is no shadow, right? If that makes sense to you, right? This isn't being projected. It's not going to lie on top of you in this direction or this direction. Therefore, the projection of V onto U would be the 0 vector. Okay. Now, technically, if you want it to be very like, technically, if you had a vector here, you might have literally a dot, but still it's not a vector. A dot is not a vector, so you still have a 0 vector, right? But basically we can just say that there's no shadow. There are two different formulas that can be used to find the vector that is equivalent to the projection of V onto U. So basically that's just saying, here's two ways to figure out what that projection vector would be. Here's two ways of figuring out that gray shadow vector. So again, you just have to be careful if you have Cartesian vectors or geometric vectors like we talked about on that previous page. So a Cartesian vector, again, is if you have square brackets given, right? So for a geometric vector, your projection formula, projection of V onto U, is going to be equal to the magnitude of V. So this one, the projection of V, right? The vector that's being projected. The magnitude of V times the cos of theta multiplied by the direction. And again, you'll see some examples. We won't even actually be doing this work. It's basically just saying again that if theta is less than 90 degrees, it's going to be going in the same direction as just saying that it's going to be positive. And if your angle's between 90 and 180, it's going to be going in the opposite direction, and then you're going to be negative. We'll see an example. You won't even have to really use this. And for Cartesian vectors, again, the projection of V onto U is equal to this magnitude here would be, again, the dot product of the V vector with the U vector. So the vector that's being projected dotted with the vector that you're projecting onto, divided by, it's always the vector that you're being projected onto is always at the bottom, and two of them. So the U vector dotted with the U vector and then multiplied by, again, the U vector, which is giving us our magnitude, right? Dot product is going to give us magnitude. Magnitude is going to be a scalar value multiplied by the direction of the vector. Like always, things will make more sense when we actually get into an example, and then we'll refer back to these, okay, as we're doing them. Same with this box, literally. There's a lot being said here. It's actually quite simple, and I'll refer back to the box when we do it. So again, this is just saying if I was figuring out the magnitude of something, the length of something, it would always be a positive value. Hence why we have like these absolute value signs around it if I'm solving for the magnitude. So if I'm between 0 and 90, we already said that my answer is going to be positive, right? Because I'm lying on top of that ground vector, if you will. My answer is going to be positive. So the projection of V onto U is equal to, again, the magnitude of the V vector times cos of theta. But if that angle was between 90 and 180 degrees, your answer should be negative, right? You would get a negative answer. So if I was getting the magnitude of something, it would be positive. So just saying that we'd have to introduce that negative back in order to have a negative value. But again, when I get to that example, I'll refer back to this box. So you're like, oh, that's what that was saying. Okay, here's a formula you'll be using a lot today in the homework. So in order to figure out the angle between two vectors, between two Cartesian vectors, so we're just calling that angle theta. Okay, so I have the vector U, I have the vector V. I don't think that should have been a double-sided. That should just be vector V. Use the formula. Cos of theta is equal to the dot product of the U vector dotted with the V vector. Again, over top of the magnitude of the U vector multiplied with the magnitude of the V vector. And where are we getting this? And again, I guess just to show that next step, if we're going to solve for an angle, right, we'd have to have, I just put that as angle. Angle theta would be the cos inverse, right, of this. You've got that step, you get down to cos theta equals a value, then you need to do the inverse of that to turn it into an angle, right? And where's this formula coming from? We're just rearranging the dot product formula from 7.2. So rearranging the dot product, I'll write it out here and then you'll see the connection. u vector dotted with v vector is equal to the magnitude of u multiplied with the magnitude of v times cos of theta. So do you see how if I was to divide by the magnitude of u and the magnitude of v, divide by, I end up with cos theta. So that's where that's coming from. Okay, let's go to some examples. So the first one is going to be referring all the way back to, I'll just clear everything, work that's being done. So we're going to the first example here. We just need to decide, are we talking about Cartesian vectors or geometric vectors here? Angela has entered the wheelchair division of a marathon race. While training, she races her wheelchair up a 300-meter hill with a constant force of 500 newtons being applied. And the angle is 30 degrees to the surface of the hill. Figure out the work that Angela's doing, the mechanical work that's being done. Okay, so if I write out my formula, the work that's being done is equal to the magnitude of the displacement multiplied by the magnitude of my force vector multiplied with cos of the angle that it's talking about. So my displacement is what? How far am I going? I have 300 meters. I can write the meters in or not. It might just help me with answering the question, you'll see. And then the force that's being applied was a constant force of 500 newtons. So I could write the newtons in as well, multiplied with the cos of 30 degrees. Okay. This section here, right? Your force vector multiplied by cos of theta. Don't forget that's the horizontal vector component, right? Horizontal vector component. I'm just going to put COMP being multiplied with your displacement. So if you plug that in, I get 129,903.8. And again, that's where the units are helping you, right? So you have Newton meters. But if you remember in the last video or 7.1, I believe, we really changed Newton meters into joules. So 129,903.8 joules. You can just put a capital J. And if we need to, I can kind of draw the hill here for you. I'm going to make it a little bit bigger. So just make sure you're listening, because so the writing's not too small in there. So we have our hill. This is our hill is 300 meters. We have the wheelchair here. Again, I'm not going to draw. We have we're parallel to the hill. And then we have our 30 degrees applied at an angle of 30 degrees to the surface of the hill. So 30 degrees here. There's our 30 degrees. That force is being applied at 500 newtons is up here. And so then this vector here, right, the horizontal, would be this 500 cos of 30 degrees. I'll just write that right here. 500 cos of 30 degrees, but then just put an arrow going to here, just so the blue doesn't cut it off. So again, that's the horizontal component that I was talking about before. Okay. So moving on to, we've got 2 and 3 for examples. So I think we can do this all in one video. Okay, figure out the angle between vectors A. We know it's a Cartesian vector because we have our square brackets here, -3 and 8. So that's the horizontal and vertical component, right? And your vector B is 7 and -1. So how do I figure out the angle in between them? So again, if we just go back, which I'll do now before I start writing, we are just looking at, again, determine the angle between two Cartesian vectors. There's your formula. We have two Cartesian vectors, right, because of the square back bracket. So just writing the, let's say, generic formula first, and then I'll tweak it to the question just so you can relate it to the other sheet, was vector u dotted with vector v. Make sure you're writing down u's and v's because they're very similar to each other, right, correctly. The magnitude of u multiplied by the magnitude of v, and that's it. So now we're just going to turn u into a and v into b. So that would be equal to, in this case, the a vector dotted with the b vector over top of the magnitude of a multiplied with the magnitude of b. So there's some work, some calculations that we have to figure out now before I'll go ahead and plug these in, right? So kind of off to the side, let's do the dot product of the two Cartesian vectors. So again, I have, let's just write out a dotted with b. Vectors would be equal to the a vector -3, 8 dotted with the b vector 7 and -1. And then how do we dot or multiply Cartesian vectors together, right? You multiply your x values together or horizontal components together, and then you multiply your y values together. And then you don't write the square brackets anymore because you're just going to work out to get a scalar. So I have -3 times 7, and then we're adding to that 8 times -1. So that's going to be -21 plus -8. And again, if you've got the plus and the negative beside each other, it might be nice just to keep that in brackets, right? So then I end up with the scalar value of -29. So I've got my numerator part, but I also need to figure out the magnitude of A and the magnitude of B, right? So let's do that off to the side as well. So the magnitude of A is just the coordinates of the components of -3 and 8. So it's just the square root of -3 squared, right? Just like getting a line, plus 8 squared. So -3 squared is 9 plus 64. And that ends up being the square root of 73. And you'll see why in a minute, but I would just leave it at that. Even if it can go be simplified further, you can do whatever you want. Just my suggestion would be to leave it like that. And then the magnitude of B would be equal to the square root of your horizontal component, or x squared, plus -1 squared. So that would be 49 plus 1, which just equals the square root of 50. And again, you'll see why I leave it like that. So going back to our formula now that I have all my pieces, the vector A dotted with vector B is -29 as my numerator, right? The magnitude of vector A in length is the square root of 73, if you will, multiplied with, dotted or multiplied with, the magnitude of vector B, the square root of 50. So then what I would do is you can actually just take 73 multiplied by 50 and put that all under one square root sign. So 73 times 50 is 3650. Then you can just take the square root of that if you would like. You can do that first, right? Take -29. I don't have that in my notes. So here, let me just bring up, if I take the square root of 3650 square root, I get 60.4. So again, you could have here -29 over 60. It's nice to put kind of 4 decimals when you're trying to get an angle. So let's say I would actually do 4152 technically, or again, you can bypass this step completely, because then again, to get an angle theta, you're going to do the cos inverse. So I can just write down the cos inverse of bracket -29 over the square root of 3650. And then it just depends on how nice and helpful your calculator is, right? Because I have a calculator like a TI 83 or 84, if you ever did that in class in grade 9 or 10 or so. where you can plug all this step in and it gives you the answer. Your calculator might do that as well. And if not, then you might want to write that step down. So again, just make sure you know how your calculator works, but you should end up with 118.7. So I would be pausing this and trying it right now to make sure that you know that's not going to give you incorrect answers to have a calculator issue when doing these questions. So that's it. I've calculated the angle between those two vectors. And so that angle is 118.7. Okay, so I know that that angle is going to be between 90 and 180, right? So now number 3. Given that I have vector -1 and 4, and vector D is 6 and 5, determine for me the projection of C onto D. So again, these are Cartesian vectors, and then we're going to figure out the magnitude of the answer we figured out here, right? The magnitude of that projection. So I'm trying to figure out to write this out, right? The projection of C, so C kind of remains the same size here. The projection of C onto D. And again, what you're projecting onto is kind of the smaller subscript. So if I go back to my formula here, Cartesian vectors, trying to figure out the projection. Again, that's what we were talking about right here. Sorry, I skipped it. Right here, the projection of C onto D is this formula. So C dotted with D over top of D dotted with D vectors on the bottom. So that's where we're headed, multiplied by the direction of our D vector. So where are we here? Right there. So let's write that out just in terms of vectors C and D, right? So the projection of C onto D is going to be equal to, put brackets around everything, C vector dotted with D vector over top of, now it is always like, let's say the subscript one, the projection of C onto D. So D is, let's just say again, kind of your ground vector. Where am I? Your C vector dotted with your D vector divided by my D vector dotted with my D vector. What I was saying was whatever is the subscript there. Multiplied by your D vector. Okay, so at first I'm just going to fill in what's in the brackets because there's, let's say, a lot of information going on here, and just carry on the D vector until I need to plug it in, and then I can just plug in 6 and 5 there. So what is my Cartesian vector? C is -1, 4. So let's have brackets here, rounded brackets. -1, 4, dotted with D, 6, 5. Right, over top of, sorry, the D vector, 6, 5. It'll get cleaned up, dotted with that same, it's the vector itself, D, 6, 5. And like I said, for now, let's just do this because it's quicker, right? So then multiplying, I have -1 times 6 would be -6 added to, and you can write down all the steps if you want, right? 4 times 5, multiplying kind of my y's or my vertical components together would be 20. Same thing for the denominator. I have 6 multiplied with 6 would be 36, and I'm going to add 5 times 5, which is 25, and I'm going to multiply that with my D vector. Okay, so one more step. Again, when I'm multiplying two Cartesian vectors together, I end up with a scalar. So same thing, if you have a numerator and denominator, you're going to end up with a scalar. So I have -6 plus 20 is 14. Sorry, I'm squishing it in here. Over 36 plus 25, 61. So I can just keep that in brackets. And now, okay, my D vector is 6, 5. So I'm just going to kind of move this up here, okay? So again, now you can just do distributive property. Just take this singular value of 14 over 61 and multiply it in with my horizontal component and my vertical component. So 14 times 6 is, and we're going to end up with a vector. So 14 times 6 is 84. 16 times technically 1, right, over 61. And then 14 times 5 is 70 over 61. And I mean, if you wanted to, you could turn those into decimal values. So the answer to this, when I'm projecting C onto D, right, I end up with, if you look, they're both positive values. So the resulting vector, then I would know, is going in the same direction, right, as my ground vector, D. They're going in the same direction. The shadow is laying on top of, let's say, the ground vector, right, because they were both positive. So now to figure out the magnitude of this projection vector, I just put my absolute value sign, projection, right, of the same C vector onto D, projection of C onto D is going to be the magnitude of my resulting vector. 84 over 61 and 70 over 61. There we go. So to get the magnitude, I'm getting my length, right? So I have to do here kind of a large absolute value sign of this value squared plus this value squared. So again, 84 over 61 squared added to 70 over 61 squared. So I will do those parts for you, just double check, right? So 84 squared, I have 7,056 over 61 squared is 3721. 3721 over 70 squared is 4,900. Over that same 61 squared, 3721. So then I keep the same denominator and just add across the top, right? So then I end up with the square root of, I have 11,956 over that same denominator, 3721. And now I can turn that into a decimal value. So I have approximately 1.79 units. Because there's no like lengths given to me, right? No units, so you can just say units. So that's the length of your shadow, if you will, right? So that's the length of the projection vector, 1.79 units. Okay, and one more to do here. What if I was given, what if my vectors were drawn here? So just one example of that. For the following, determine again what the projection vector would be. So the projection of U, this is the projection vector and it's being projected onto V, or what I would call kind of your ground vector, right? So where's the shadow going to end up if I'm between 90 and 180? Because you can see there 98 degrees. You can kind of already foreshadow what's going to happen, right? And then let's figure out the magnitude and that length of that shadow vector, of the projection vector. So the projection of U onto V, let's write it out here as the projection, again, of U, kind of regular size. The V should be smaller. It's just hard on my tablet. So the projection of U onto V is going to be the magnitude of U multiplied by cos theta. So it's the magnitude of your projection, the vector that's being projected, right? The one that the rays are going towards to create the shadow. So the projection of U and then just times by cos of your angle because you're given the drawing. So then the magnitude of u we have right here, the magnitude of u, the length is 15 times cos of 98. And 15 times cos of 98 is negative 2.1. So if my projection vector turns out to be negative, what's that telling me? That I am 2.1 units going in the opposite direction of my v vector. So because it's dotted, I can't actually choose a line, but I'm trying to just go, let's say, right like this. And this shadow would be directly down. So it would go about that far, let's say, that this would be my projected vector, my shadow vector there. So you can see I'm going in the opposite direction of vector v, which makes sense, right? Because I was bigger than 90 degrees. Okay, so this magnitude, I'll refer to it now and then maybe I'll refer back to it again, or just you can go back to it at the end of the question, is where I'm talking about this box. The magnitude always has to be positive. If you're getting the magnitude of something, a length, it's always going to be a positive, just like speed is always positive, right? But we're talking about here, how do I introduce a negative back when I need to? And that's what I'm talking about in this question here. So just refer this part B back to that box. So if I'm getting the magnitude of this projection, let's again write that out with our magnitude like absolute value symbols. So the projection of u onto smaller subscript v is going to be equal to the magnitude of u times the cos of theta. Well, I already have that value here as negative 2.1. So then that would be, let's say, right, the magnitude, like the absolute value of negative 2.1 of my answer here, but that's going to be a positive answer, right? Which is going to be 2.1. So if I just had here without the absolute value, without getting the magnitude, if I just had this as writing down what my answer was here, negative 2.1, right? I'd have to multiply it by another negative to turn it positive. And that's all that box is saying here. If you come up to the top, in here, I have to negate the magnitude portion, right? And add the negative in if I need to. Add another negative in order to turn the magnitude length to be positive. So if your answer is negative, all it's saying is, and the same thing if you were to put like absolute value signs around it, right? It's just saying that make sure your magnitude is always positive. So if your original answer was negative, do what you need to do to turn it positive. So just multiply it by another negative, right? Which is like that, or just keep the absolute value signs around it and turn it into a 2.1 because length is always positive. So magnitude, right, is 2.1. Let's just write out here units in length, and then I'll write out here must be positive. Okay,